So for some function f of x, the difference quotient that we have here is defined as f of x plus h minus f of x divided by h, where what this tells us is something like how much our function changes, looking at a picture, in terms of a gap with width. Oh god, that's bad phrasing. H, where h is some value other than 0, as for 1, that would cause that whole thing to be undefined, and for 2, it wouldn't be a very interesting gap, now would it? However, there is something very important that happens there as we make that gap small, and we'll talk about that in just a minute, but first, we're going to get an example here, practicing with how we can simplify a difference quotient. So we want to find and simplify the difference quotient for the function f of x equals 3x squared minus 5x plus 4. And basically what we want to do here is plug in our h's where they need to go, then factor some things out, group, simplify, and we'll end up with some relatively nice thing, where in this case the value f of x plus h is going to have the very friendly form 3 times x plus h quantity squared minus 5 times x plus h plus 4. Usually when we're dealing with difference quotients, we don't get the very nicest values. It just sort of happens that way. This one's not so bad relative to some things we may see elsewhere. Then we just have our function f of x, so that would be minus 3x squared minus minus, so plus 5x, then minus 4, and then from here we just need to simplify. We need to combine some like terms and see what goes away. Where first thing I'm going to do is expand out all of the h terms, so that 3x plus h squared becomes a 3x squared, a 6xh, and a 3h squared. Then we have minus 5x and minus 5h, plus 4, and then f of x again. I'm not going to say what that is because it's the same thing where all of this is being divided by h, but we're going to see that as bad as that looks, a lot of stuff is going to cancel and everything that's left is going to have h terms and it won't be so bad. Because the 4's cancel, the 3x squareds will cancel, and the 5x's will cancel, leaving us with just 6xh plus 3h squared minus 5h. Like I said, we've got h's everywhere, kill those two, and we are just left with 6x plus 3h minus 5. I kept forgetting to say divided by h. That's an important piece to carry on because it is what lets us finish this problem. I don't know why I stumbled over that there. But what this type of value tells us is something a bit about an average rate of change, which we'll see more of at the end of our third section for this week. But more importantly, something very special happens with this kind of value if we let h equal to 0. And as I said at the beginning, you can't really talk about the jump if we're making h 0. You can't really talk about that function thing there if you make h equal to 0. But at this point, at the end, if we make h equal to 0, then we would end up with something manageable, something like 6x minus 5. And that might not seem like much, but that's actually a very vital value, as it would describe how much our function is changing at any point along its curve. It describes a thing called a derivative, because what we're doing right here, getting this value down at the bottom, is the technical computation of a derivative, or at least most of it, as those of you who take calculus will see. So here you can lord that over your friends who are taking calculus. Ha ha ha, you know how to compute a derivative, or at least kind of. There's a little more to it than that, but this is the main idea. Where we're going to see more of this, as I said, further on in 2.4, but this idea of slope is something that we'd like to develop a bit more first, and that's what we're going to be jumping into in 2.3.